Hello students, I am Jisha Assistant Professor from the Computer Science Department of Rajagiri School of Engineering and Technology. In this lecture, we will be dealing with some of the topics from Computer Organization and Architecture, a course under KTU for the 4th semester CSE and IT students. The topics to be covered in this lecture will be from Module 4, Cache Memory. The main contents that are being discussed in this lecture have been listed below. In our previous modules, we have already discussed the different functional units of a computer, and this involved two main components, that is the processor and main memory. Assume that some data transfer operation is to happen between these two components. That is, I want to send some data from the processor to the main memory or vice versa. Now, what is the main issue that is going to happen here? Yes, it is the speed difference. The processor is of high speed, whereas the main memory is comparatively slower. So what happens is the processor has to waste its time waiting for the main memory to complete a task. This results in wastage of the critical time of the processor. Now, how to solve this problem? To solve this problem, a very fast memory module was introduced and placed in between the processor and main memory. And this fast memory module is known as the cache memory. The cache memory can thus be defined as an architectural arrangement which makes the main memory to appear faster to the processor than it really is. And the main advantage of introducing this extra memory module is that it ensures efficient utilization of the processor time is achieved. Next, we'll see what is the working model of this cache memory. Suppose the processor wants to read some data from the main memory. The processor will issue a read request. When this read request is received, the data that is to be read, which is available in blocks in the main memory, will first be brought into the cache memory. And from the cache memory, the data will be provided to the processor. Now, what is the advantage of keeping this data in the cache memory? The advantage is that when a request for the same data comes in the future, then we don't have to go to the main memory to read this data again. Instead, the data can be read from the cache memory, which is comparatively nearer to the processor. So the time involved will be less. Now, what is the concept of working behind cache memory? It is based on a concept called locality of reference. Locality of reference is of two types. It can either be a temporal locality of reference or it can be a spatial locality of reference. The first one is based on the concept that the most recently executed instructions in a computer are likely to be executed again very soon. For example, take the case of looping statements. The statements that are present inside a loop are very likely to be executed again. Next one is spatial locality of reference. Here, it is defined as the case where the instructions with close proximity to each other or close proximity to recently executed instructions are very likely to be executed again soon. So, this is what is known as temporal and spatial locality of reference. So how this concept can be applied in the terms of cache? That is, we can talk about the temporal aspect and the spatial aspect. In temporal aspect, we can say that whenever an information item is first needed or whenever an information item is accessed by the processor first, this item can be brought into the cache memory and that item can remain there until it is needed again. Okay, next one is the spatial aspect. That is, instead of fetching just one item from the main memory to the cache, it is always useful to fetch several items or items that reside at adjacent locations to the currently accessed item together into the cache. So the two main activities that can happen inside a cache memory are hit and miss. So whenever one data item is accessed, first we will check whether the corresponding item, or in technical terms the word, is available in the cache or not. If the word is already available in the cache, then the operation will take place on that corresponding data, and this is called a hit. Whereas when I'm trying to access a word and if that data is not available in the cache, then the block of data involving that word should be first fetched from the main memory and only then I can access it. In such a case, we call it as a cache miss. When the processor wants to perform a read or a write operation from the main memory, it simply issues a read or a write request. The processor has no idea about the cache memory which is sitting in between the processor and the main memory. So when a read or write operation is performed, it is the cache control circuit who is going to perform the read operation on behalf of the main memory. For example, first let us consider a read operation. If the data that is to be read by the processor is already available in the cache, then it is called a cache hit. The data can be directly taken from the cache itself. No need to go to the main memory. Whereas if the data that is to be read from the main memory is not available in the cache, then it is called a cache miss, and that corresponding data contained block should be accessed from the main memory first to the cache, and then from the cache the data will be read to the processor. Now, the third case that can arise is, suppose I am trying to read some data and that data is not available in the cache, but it is accessed from the main memory, and now there is no space present in the cache to bring in the incoming main memory block. In that case, some blocks of the cache memory should be replaced first using some algorithms which we will discuss later, and after that the data will be provided to the main memory. Next is the write operation. If the processor wants to write some data into the main memory, in that case also the cache will be involved. And here also there are two cases that can either be a write hit or a write miss. In the case of write hit itself, there are two protocols followed. It can either be write through or write back methods. If I am following the write through method, then it means whatever data the processor wants to write into the main memory, it will be updated simultaneously in the cache as well as in the main memory. And if I am following the write back method, whatever data the processor wants to write into the main memory now will be updated only in the corresponding cache block at this moment. And when this corresponding cache block is being replaced at a future period from the cache, at that moment, by making use of a dirty bit which is set during that write process, it will be updated in the main memory. And in the case of a write miss operation, that is when I'm trying to write something into the data, and if that corresponding block is missing in the cache, then also there are two cases. We have write around and write allocation policies. Write around policy is where whatever data is to be updated, it will be updated directly in the main memory block. No changes or no updations are done in the cache because that block is not there in the cache. Whereas in the case of write allocation method, first that main memory block which is to be updated will be brought into the cache, and then the updation will be made in the cache, and at a future point of time that corresponding data can be updated in the main memory. So these are the different possible cases that can happen during a read operation and a write operation. In the case of read operation, I can either have a cache hit, cache miss, or a cache miss with a block replacement. Whereas in the case of write operation, I have write hit and write miss, where there are different protocols followed, which are write through and write back in the case of write hit, and in the case of write miss, I have write around and write allocation. In the beginning of this module, we have already discussed the memory hierarchy, and according to the hierarchy, we know that the cache memory is much smaller in size compared to the main memory. So, at a particular point of time, only some blocks of the main memory can be held in the cache. Not all the data or not all the blocks that are there in the main memory can be put inside the cache. So, which block of data of the main memory can be put into the cache. There should be some kind of a mapping possible. And to do this mapping, there should be a mapping function. Thus, we have the term mapping functions. It is defined as the correspondence between a main memory block and a block in the cache memory. So there are three kinds of mapping functions, namely direct mapping, associative mapping, and set associative mapping. Now, to study in detail about these mapping functions, let us consider an example system. This example system has got a main memory which is addressed by a 16-bit address line, and the total size of the cache that is available in this system is 2048 words. And these 2048 words are actually 128 blocks of 16 words each. That is, there will be 128 blocks and each block will contain 16 words. Okay, and the main memory of this example system will have 64K words, that is 4096 blocks of 16 words each. That is, each block in the main memory will contain 16 words. So from this example itself we can understand that the cache is much smaller compared to the main memory. So first we will see direct mapping. It is the simplest of all the three mapping functions. Here, when I want to map a main memory block into the cache, the block, suppose for example, if I am mapping block J of the main memory into the cache, it will be only be mapped into the block J modulo 128th position in the cache. For example, if I am taking block 0 from the main memory, it can be brought to 0 mode 128, that is the 0th block in the cache. Another example, if I am taking block 1, then it will be mapped into block 1 modulo 128 or the first block in the cache. Similarly, so if we can generalize it, we can say that block numbers 0, 128, 256, etc. All these blocks can only be mapped into block 0 of the cache. But only one block can come in at a time into that corresponding block. Another example, if I am taking block 1 or say block 129 or say block 257, all these can come into block 1 of the cache. So now what is our aim? How do we find out which block of the main memory is in the cache block now? Whether is it block 0 or block 128 or say block 256, which is now currently residing in block 0 of the cache. For that, we need to look into the memory address. So this is a diagrammatic representation of what we just talked about now, that is direct mapping. Here you can see the cache memory and the main memory. The cache memory, as I already said, consists of 128 blocks numbered from 0 to 127, and each block can store 16 words each. Similarly, the main memory also consists of 4096 blocks numbered from 0 to 4095, and each block can hold 16 words. Now, how is the direct mapping happening? That is, block numbers 0, 128, 256, etc. can be mapped only into block 0 of the cache. Similarly, block 1, 129, 257, etc. can be mapped only into block 1 of the cache. So this is how the mapping is going to take place. Now, suppose for example, block 0 and block 128 needs to come to the cache memory at the same time. What will happen? Both of them try to come to the cache block 0, which is not technically possible. That is, there will be some kind of an issue because they can come only to block 0 even if the rest of the 127 blocks are remaining empty in the cache. Okay, so this is how direct mapping works. Now, at a particular point of time, how will we know which block, whether it is block 0 or block 128 or block 256 of the main memory, is currently residing in the cache now? For that, we can look at the main memory address. So as mentioned in the beginning, here we are going to consider a 16-bit address line. So the memory address will also be consisting of 16 bits. Now this 16-bit memory address can be divided into three parts. A 4-bit word field, a 7-bit cache block field, and a 5-bit tag field. The least significant 4 bits in the memory address can be used to select one of the 16 words in a block that is now residing in the cache. That is, for example, if a block is now present in my cache memory, then in that block, which word I want to access, that can be specified by using the 4 bits. But for example, if my 4 bits are 0000, then it means I want to access the first word in my current block. If my 4 bits are say 1111, then that means I want to access the last word of my current cache block. Okay, next one is the 7-bit cache block field. It is used to select one of the 128 cache positions in which an incoming block must be stored. So we know that our cache memory consists of 128 positions. Into which of these 128 positions an incoming block from the main memory should be placed? That is decided using this 7-bit cache block field. For example, if my cache block field value is all the 7 bits are zeros, then it means the incoming main memory block should be placed into the block 0 of my cache. Whereas if all my 7 bits are ones, then that means the incoming main memory block should be placed into the 128th, that is last position in my cache. And the last one is the 5-bit tag field. It is used to identify which of the 32 blocks that are mapped into the same cache position is currently resident in the cache. For example, we know that there are 4096 blocks in my main memory. Out of these 4096 blocks, 32 blocks each are mapped into one cache block position. So, which of those 32 blocks are now currently residing in a particular cache block position? That can be identified using this 5-bit tag field. So the main disadvantage of direct mapping method is contention can occur. That is, if the main memory blocks 0, 128 and 256 need to be brought into the cache at the same time. They cannot come into the cache at the same time because all of them try to come into the block 0 of the cache. So there is some kind of a contention occurring. This is the disadvantage of direct mapping. So a solution to this direct mapping problem was achieved in the next method, which is known as associative mapping. Here, an incoming block from the main memory need not be mapped into a particular modulo position. Instead, it can be placed anywhere in the cache if that position is free. That is, so what do we understand from that? There is no need of a separate 7-bit cache block field in the memory address. So we only require some bits to identify which word I want to access, and the rest of the bits in the memory address can be used as tag bits. So there will be, if I am taking a 16-bit memory address, only 4 bits are needed for identifying the word, whereas the rest of the 12 bits can be used as tag bits. Okay, so and here the search of the complete cache has to be done in order to identify whether a block is there in the cache or not. That would be an issue of this method, but compared to the first method, there is no issue of contention occurring. That is, even if there is free space available in the cache, some blocks which are mapped into the same cache block cannot come in. But that issue is solved here. But instead, the problem here would be that if I want to identify a block that is residing in the cache, the complete cache memory has to be searched. So as I have already mentioned, in the case of associate mapping, there is no need of separate 7 bits for identifying the cache block field. Instead, we require only 2 kinds of bits, that is 4 bits for identifying a word from the corresponding block, and 12 bits for identifying the position into which the main memory block has been mapped. So 12 bits for tag and 4 bits for word. So what is the disadvantage of associative mapping? The main disadvantage is the search time that is involved to identify where a particular block is in the cache is much more compared to direct mapping. You have to search through the full cache block to find out a corresponding entry. Now to overcome this disadvantage, we go for the third method, which is known as set associative mapping. It is actually a combination of the first two methods, that is a combination of the concepts used in direct mapping and the concepts used in associative mapping. Here the new thing that is introduced is sets. So here the cache blocks are grouped into sets. The set size may be 2 or set size may be 4, or it can be any size. It can be of size say k. So if I am having a set of size k, then that means that set will contain k number of blocks. And when a memory block is coming from the main memory into the cache, the incoming block can be mapped into a particular set, and inside that set it can go to any of the freely available blocks. So it is combining the concepts of direct mapping as well as associative mapping. Now what is the advantage of this method? It uses fewer tags compared to associate mapping, but it is found to be more flexible than direct mapping, because we are not restricting the main memory blocks into one particular block. Instead, we are only restricting them to a particular set. Now inside that set itself, they can go in. Suppose if a particular block is filled, it can go into another block which is free. This is what is known as set associative mapping. So this is a diagrammatic representation of set associative mapping. In this we have a two-way set associative mapping. That is, the number of blocks that are involved in a particular set are 2. So here the main memory blocks 0, block 64, block 128, etc. All these kind of blocks will be mapped into set 0 of cache of the cache memory. Similarly, block 1, block 65, block 129, etc. will be mapped into set 1 of the cache. Now inside set 0 itself, there will be two block spaces available. So suppose for example block 0 and block 64 wants to come in at the same time into the cache, they can come in and they can occupy either block 0 or block 1 of the set 0 of the cache. Now if again block 128 also wants to come in, and if block 0 and block 1 are filled, then there is a issue of contention. So compared to direct mapping, it is more flexible. That is the advantage here. And also if you want to search for a block, you don't have to search through the full cache. Instead you can search inside the given set, and to identify which is the given set, the memory address can be split into 3 parts. The least significant 4 bits can be used to identify which word you want to read from a particular block. And since there are 64 sets possible in the cache, there are 6 bits set aside to identify the set to which the corresponding cache block the main memory block can be mapped, and the last 6 bits, the most significant 6 bits, can be used as a tag to identify the cache block into which the main memory block has been mapped. So with that, we have completed the 3 different mapping functions. Now we just need to make some comparisons. That is, in direct mapping, the position of each block is already predetermined based on a function, based on a formula. That is, for a block j that is coming from the main memory, it is always mapped into j modulo 128. So there is no need of any replacement strategies. If the corresponding cache block is full, then it will either have to be overwritten or some waiting procedures have to be followed. Whereas in associative and set associative methods, the block position is not predetermined. We have to place the block into a particular location. That is, when the cache is full and if the new blocks are brought into cache, then the cache controller must decide which of the old blocks have to be replaced. So some mechanisms must be in place so that I can replace an already existing block in the cache. So, whenever a block is to be overwritten, it is always better to override the one which has not been used for the longest amount of time. So, if we can find out which is the oldest block in the cache, and if we can remove it, then we can maintain the temporal aspect and spatial aspects of cache memory concept as well. And this procedure is called the least recently used technique, and the block which is removed based on this concept is called the LRU block, or least recently used block, and the technique is called the LRU algorithm. The cache controller will track the references to all the blocks that have been made in the past with the help of a block counter, and based on that he will find out which is the oldest referred block, and based on that, that corresponding block can be removed from the cache, and the new incoming blocks from the main memory can be placed into the cache. Now, two main factors that can be considered for analyzing the performance of a cache memory can be the best possible performance at low cost, and this is called the price performance ratio. The performance of a cache memory will always depend on how fast the machine instructions are brought into the processor and how fast they can be executed. Okay, so this is what is known as price performance ratio. Two other values which can be used to determine the performance of a cache memory are hit rate and miss penalty. Hit rate is defined as the number of hits which are stated as a fraction of all the attempted accesses. That is, when I'm trying to access a word from the cache memory, what is the chance that I will be able to access the word from the cache at the first access itself? That is what is known as hit rate. Whereas miss penalty can be defined as the extra time that is taken to bring the desired information into the cache if it is currently not present in the cache. That is what is known as miss penalty. And always the goal will be to increase the hit rate and decrease the miss penalty. So with that, we come to the end of this online lecture video, which was basically about cache memory. So initially we discussed about the need for a cache memory inside the computer. Then we saw what are the two main concepts based on which cache memory works, that is the temporal locality of reference and spatial locality of reference. Then we saw the working model of the cache memory. Then we saw how the different mapping functions, that is direct mapping, associative mapping and set associative mapping, can be used to map a main memory block into the cache memory block. And also we saw two different performance consideration terms like the price performance ratio, hit rate and miss penalty. I hope all of you will benefit from this presentation. Thank you.